Thank you, Pierre, for the introduction and also for the opportunity to speak at this seminar. As you can see, this work was done during my time in Austin, and some of it is joint with Alexis Vasseur. And we were studying the 3D quasi-geostrophic system, which is perhaps not the most familiar of fluid equations. And we were able to prove several theorems in a variety of settings. And I will present all of those to you today. And rather than focus on the details that pertain to just one, I hope to give you some of the ideas that recurred throughout. And then when appropriate, I'll make some comments about some of the specific settings. All right. So the first thing I need to do will be introduce the equations that I'm studying. And that being done, I will be able to tell you the main results that we were able to prove. They can fall into two categories. One is for the viscous version of this model. And in that case, we have a global existence theorem for smooth solutions. And in the inviscid case, we have a few results. Global existence of weak solutions, non-uniqueness via convex integration. And then also, we were studying the boundary conditions, the physical boundary conditions that one would impose when studying this model on a cylinder. And then when I have a little more time, I will tell you some of the main tools that we use. The first is the reformulation of the problem. And then I'll make a remark about the model on a bounded domain, where we have the physical boundary conditions. And we had a cute elliptic problem arise out of that. And then finally, I'll say a few things about the non-uniqueness theorem. All right. So the physical scenario that I'm interested in describing is atmospheric or oceanic circulation, which is occurring over large spatial and temporal scales. So if I'm describing a fluid, my baseline is the Navier-Stokes or Euler equations. And so what I'm going to do is show you how the quasi-geostrophic system relates to these more familiar equations. All right, so here I have written the Euler equations with a few adjustments. The first is the Boussinesq approximation, and that says that changes in density are significant insofar as they're magnified by gravity. So I have the density appearing in the equation for the vertical velocity and not for the horizontal velocities. And I have the Coriolis force as well, and that comes from the effect of the rotation of the Earth, and that force is exerted perpendicular to the velocity and the axis of rotation. So I have a plus u in the equation for v and a minus v in the equation for u. And this parameter c quantifies the strength of this effect. And of course, I have incompressibility and transport of the density. All right, so of course, Navier-Stokes and Euler in 3 dimensions are quite difficult to study. And so the goal will be to find a simplified model, which is the quasi-geostrophic system, that still accurately captures the physical characteristics of stratified rotating flows. And our method for pulling the quasi-geostrophic system out of Euler here will be to first adimensionalize the equations. So I picked a characteristic length and velocity scale. And the small parameter that appears is this parameter epsilon, which is called the Rossby number. And it's inversely proportional to the strength of the Coriolis force. And the goal will be to take an asymptotic limit as epsilon goes to 0, because I'm interested in the dynamics when the effect of the Coriolis force is significant. So I want to take this parameter c to infinity, i.e. epsilon to 0. All right, so to take this asymptotic limit, I won't write out all the steps, but the idea is that I expand all the terms in my Euler equations with respect to epsilon, and then I collect all the terms that have the same order of epsilon. All right. And what we find upon doing that is that to leading order, we have what's called the geostrophic balance. And this says that the wind velocity is stratified and orthogonal to the gradient of pressure. So this is a level set of the pressure. Here's the gradient of pressure. And for now, I only have to differentiate in x and y because my velocity is stratified, meaning that it's purely horizontal and it's orthogonal to this gradient. So to leading order, this is what I find. All right, this is a little bit too simplified, and so I want to pass to the next leading order in epsilon, and what I get at the next leading order in epsilon is the quasi-geostrophic balance. So not as simple as the geostrophic balance, but still tractable and captures the physical quantities, the physical characteristics that I'm interested in. All right, so the next leading order in epsilon is my set of equations, and let me now show those to you. All right. So my equations are posed in terms of a stream function psi. Psi comes from the pressure from my Euler equations, but I'll just adopt the classical notation for QG and refer to the stream function as psi. And as I said, the fluid velocity is stratified, so the third component is 0. And it's divergence-free and given by the perpendicular gradient in x and y of my potential psi. In terms of notation, I have every time I put a bar above a differential operator, it means that I'm differentiating in x and y only and not in z. So there's no complex variables or anything like that with the bar. I will need the Neumann condition at z equals 0. So we're imagining that our system is posed in the upper half space, and here's d nu psi at z equals 0. And the equations that we have then, let's parse these, and let me also write them here since we will refer to them throughout, and it will help you remember. All right. So the first equation is simply a transport equation for the vorticity. And this is valid in the interior of my domain, so for z greater than 0. Right now, I'm just imagining that omega is the upper half space. Sorry, omega is all of R2, so that my physical domain is the upper half space. And at z equals 0, we have on the left-hand side transport of the Neumann derivative. And on the right-hand side, we have this term r times the Laplacian in x and y of psi. So r for me is just 0 or 1. And it's 0 if I started from the Euler equations, and it's 1 if I started from Navier-Stokes. And the reason the dissipative term only shows up on the boundary is, of course, that the effects of the dissipation are magnified at my physical boundary. All right, so if I look at these equations, the difficulty throughout the analysis will generally be at the boundary z equals 0. And if I have no dissipation here, then this is pure transport, and I have no regularizing effects. But even if I have this dissipative term here, it's a Laplacian bar in psi, not a Laplacian bar on d nu psi. So I can't treat this as a heat equation. My dissipative effects are not as strong as one might hope. All right, so these are the equations that we're studying then. And our main results, which I can now tell you about. The first, and I'll keep track of them over here. The first is a global existence theorem for smooth solutions in the viscous case. So viscous model, global smooth solutions. All right, so my theorem says that if I specify an initial data belonging to HS, then I have a unique global and time classical solution emanating from that initial data. And the regularity of the initial data is propagated throughout time. And if I look at I should say that obviously this tells me that if my initial data is smooth, then I have a unique smooth solution in time and space. And if I look at the equation for the transport of vorticity, I have no regularizing effect here. And so the strongest theorem that I could hope to prove is that the regularity of the initial data is preserved, and that's indeed what we showed. And how this relates to perhaps more familiar results, so I'll explain this a little bit more later, but when the initial data is harmonic, my system reduces down to 2D SQG, which has been extensively studied. And global existence for the critically dissipative 2D SQG has been known for about 10 years now. There's a number of proofs, one of my advisor, Vasseur and Caffarelli, and Vlad and Peter Constantine, and Kislev and Nazarov, and Volberg. All right, so this theorem, in some sense, is the generalization of those theorems to the system with non-trivial interior vorticity. All right, so let's move then to the inviscid case. So the inviscid model in the upper half space, so no dissipation on the right-hand side there. And this is a theorem for the global existence of weak solutions. And what it says is that if I specify an initial vorticity and Neumann condition, then I have a global and time weak solution where the gradient of psi stays uniformly bounded in the Lebesgue space that I would get by simply solving the elliptic problem with data in those Lebesgue spaces. All right, so Vasseur and Marjolaine Poyle had already built weak solutions for this system in the case when the initial data belongs to L2. But the difficulty here will be how to define weak solutions for small p and q. So if I don't have much integrability on the data, I will need to come up with a notion of weak solution, because if I simply take this equation and multiply by a test function and integrate by parts, so I can pass this derivative from the nonlinear term onto the test function, and then I have perpendicular gradient of psi times the Neumann derivative of psi. And if I wanted to make sense of this, I would need that these guys are in L2, and I could just use Holder's inequality. But my theorem applies to cases when I have less integrability than that. So what I really need then is an appropriate notion of weak solution which elides this difficulty. And that'll be sort of the key point for this theorem. All right, so before I can tell you a little bit more about weak solutions for this inviscid model, I want to connect back to 2D SQG. So if I impose that my initial data is harmonic, then due to the transport equation, I will have that property is preserved in time. And so I have a harmonic function in the upper half space, which tells me that at the boundary z equals 0, I know that the normal derivative in z is equal to the half Laplacian in x and y. and the usual notation for that in SQG is theta. And then my velocity is the perpendicular gradient in x and y of psi, which should be the perpendicular Riesz transform of the half Laplacian, i.e. the perpendicular Riesz transform then of theta. And so my equation then at the boundary becomes this active scalar equation, dt theta plus u dot gradient theta equals 0, where my constitutive law is u equals the perpendicular Riesz transform of theta. And so this is 2D inviscid SQG as a special case of 3D QG where the interior vorticity vanishes. And 2D SQG has been studied for a long time, definitely by people here. And weak solutions were first constructed by Resnick in L2 back in '95. And then some years later, Marchand did it for LP for p bigger than 4/3. And if I look at this exponent here that Marchand has, it's 4/3, which is the same that I have for the 3D case. So that really shows that we recover the strength of the theorem in the case when the initial data is harmonic. All right, so then a natural question then is, given these weak solutions that people constructed to 2D SQG, how do they connect to the notion of weak solution that I'm going to use for the full 3D model? And the answer is that they correspond quite nicely. So in the case when the stream function is harmonic, the weak solutions constructed to SQG are weak solutions in the sense that I'm going to use for the 3D model and vice versa. And if I have enough integrability on the vorticity and the Neumann derivative, then the weak solutions that I will build to 3D QG are going to satisfy the transport equation in the usual sense. All right, so global weak solutions, let's say, and properties of those weak solutions. And then finally, in the upper half space, this theorem tells me when the energy is conserved. So the natural energy for the inviscid model is the gradient of psi. And this theorem says that if I have basically more than 1/3 of a derivative in x and y uniformly in t and z, then I have the conservation of the energy. And this is, of course, the analog of the Constantine-Ur-Titi result. But you'll notice that I only require the regularity in x and y, and that's basically because my system is stratified. So I only need to integrate by parts then in x and y to show that the energy is conserved. All right, so let's switch settings and imagine that instead of being in the upper half space, I have some bounded set in R2, and I'm posing the equations in an infinite cylinder above that set. I know that in the interior, I have that Laplacian psi is whatever it is, and on the boundary, d nu psi is whatever it is. But if I want to solve an elliptic problem in this cylinder, I need lateral boundary conditions. So and the question is, what are the natural boundary conditions? And what we found is that the natural boundary conditions are a strange mix of Dirichlet-Neumann, which I will show you. So what do we have? Let me draw a picture to help parse this. So if I fix a cross section, and I look at the values of psi on the boundary of that cross section. So this is psi restricted to d omega cross some value of z. Psi doesn't vary with respect to x and y. So then what this says is that up and down the lateral boundary, psi only varies with respect to z. And so it looks like I have one extra degree of freedom. Maybe I can choose a convenient value on the lateral boundary. But we found one other boundary condition, which is a little quirky, certainly. And what it says is that if I look at this cross-section and I integrate the outward pointing normal derivative of psi around this cross-section, that quantity is preserved in time.
Does that boundary condition correspond to an actual velocity condition?
Yes, so I was just about to, no, that's a good question. I was about to explain what I meant by natural. So what we did is we started with the Euler equations and assumed that the velocity didn't penetrate the wall. And then we carried that assumption through the asymptotic limit, and this is what popped out. All right, and so the theorem for the inviscid model on a cylinder is that we have boundary conditions and global weak solutions. And then just this past year, we also proved that given appropriate smoothness and compatibility assumptions on the initial data, I have local and time classical solutions. And the difficulty there is that my domain now has a corner at z equals 0 from this cylinder. So I'm essentially then tasked with proving an elliptic regularity theorem in a domain with a corner. And so I expect to have some compatibility conditions at the corner. And I'll say a little bit more about that later.
This time you're only local time.
Correct. Well, I have no dissipation. Dissipation, yes, it would require a little more thinking about what happens with the boundary layers. All right, and then finally, we have a non-uniqueness theorem. So for this, I'll pose the equations on the torus in x and y, and then 0 to 2 pi in z. And the theorem says that in Holder regularity classes below 1/5, I have non-uniqueness and dissipation of energy. All right, and the energy conservation theorem that I had said that energy was conserved above Holder regularity 1/3, and this theorem only goes to 1/5. So I have a gap in between where energy dissipates and where energy is conserved. And roughly speaking, that gap is there because for the same reason that Onsager is not yet settled for 2D Euler. Namely, in 2D Euler, I have some constraints on the type of building blocks that I can use for my convex integration scheme. And I'll show you a little bit more later that I seem to have those same constraints for 3D QG. All right, so those are the main theorems that we proved. And now let me tell you some of the main ideas that we used throughout. And the first thing is, of course, what are my a priori estimates for the inviscid model? Well, due to the divergence-free structure of the transport, I have preservation of the Lebesgue norms of the vorticity and the Neumann derivative. All right, but the issue with these estimates is that if I have a uniformly bounded sequence of dz psi at z equals 0, I can pass to a weak limit, but I won't have strong convergence for either the velocity or the Neumann derivative at z equals 0, which means that I have some issues with compactness at the boundary. All right, so the way to get around this lack of compactness is to find a reformulation of the system. And that's the next tool that we used repeatedly. So the formulation I have here is at the level of the vorticity and the Neumann derivative. And so I could expect to look for a reformulation of the equations at the level of the gradient of psi rather than the vorticity and the Neumann derivative. And the analogy here is, of course, with the Euler equations in either vorticity or velocity form. So this is like Euler in vorticity form, and I'm looking for the appropriate reformulation. All right, so I should expect that if I have an equation where on the left-hand side I have transport of the gradient, I expect a Lagrange multiplier, which will act to preserve this gradient structure, just like how in Euler I have the Lagrange multiplier being the pressure to enforce the incompressibility. But ignoring the Lagrange multiplier for a second, let's just see what happens if I look at the advective derivative of the gradient. So if I take the divergence of this equation, when the divergence lands on the velocity, I have the perpendicular gradient of gradient psi dotted into the regular gradient of gradient psi, and I have orthogonality. And so what I get is then just the transport equation for the vorticity. All right, so that looks good. And if I then take the trace of this equation at z equals 0, what I have is exactly the transport equation for dz psi at z equals 0. All right, so I will need a Lagrange multiplier on the right-hand side, which acts to enforce this gradient structure, and I need it to be in the kernel of these two operations. So I need it to disappear when I take the divergence, and I need it to disappear when I take the trace at z equals 0. And so it's not too hard to guess what it is. If it disappears when I take the divergence, it should be a curl. And if I want the third component to be 0, I have to enforce that. And so my Lagrange multiplier is then the curl of Q. And of course, I can write curl of Q in terms of a projection operator applied to the nonlinear term. But I won't use that formulation for now. I'll use this formulation. All right, so then the notion of weak solution then that I will use is, of course, take this equation and multiply by the gradient of a test function. If I multiply by the gradient of a test function, the right-hand side will disappear because of these two facts. And I define then my weak solutions at the level of the gradient, and I have the compactness that I need to pass to the limit in this nonlinear term. And notice that I don't claim that I have strong convergence at z equals 0 because I probably don't. But I don't need that in order to build my weak solutions. All right, so let me focus now on the model posed in the cylinder. All right, so I said that our boundary conditions were that on the lateral boundary, psi only depended on t and z. And then I have this funny condition on the average Neumann value of psi on the lateral boundary. And if I think about that in terms of an elliptic problem, what the elliptic problem then that I'm solving is I have Laplacian in the interior because I have transport of vorticity. I have a Neumann derivative at z equals 0 because I have transport of the Neumann derivative. And then I have this condition, so u of x, y, z equals u of z on the lateral boundary. And if this quantity is preserved in time, then it's specified by the initial data. So I need to be able to solve an elliptic problem where this value is prescribed. All right, so the way we went about this was to find the right Hilbert space. And our Hilbert space, is simply U in H1, for which U restricted to the lateral boundary only depends on Z. And if I integrate by parts in this Hilbert space, So I have gradient u dot gradient v in my cylinder. What happens? I have v Laplacian of u, and I have normal derivative of u, v at z equals 0. And I also have, let's see, I have the integral from 0 to infinity, integral over d omega, the normal horizontal pointing outward normal of u, and then times v. All right, but I notice that v belongs to this Hilbert space, so it only depends on z. And so I can move v to my dz integral. And then this is the data then that's prescribed by the problem, the average value of the normal derivative of u around the boundary at that height z, dz. All right, so now I'm in the right Hilbert space to solve this elliptic problem. And so what we were able to prove is if I specify initial data which belong to L2, then u belongs to H1.5. And that's good enough to build weak solutions because then I have compactness at the level of the gradient of u. All right, but if I want to build smooth solutions, I will need higher regularity on u. And so when we built the smooth solutions, we had to strengthen this theorem a little bit. And what we showed is that if I put the initial data in H4, then I have u in H5.5. If I were just solving a Neumann problem, like let's say I was solving Laplace u equals 0 and the normal derivative of u was in L2, then by the trace I would expect gradient of u to be in H1/2 or u to be in H3/2. So that's the normal elliptic regularity. It's probable that if I put more regularity on F, G, and J, then I could get more regularity. But the difficulty is in the compatibility conditions. And I can think of that even just in the context of a standard Neumann problem. Let's say I was on a square and I had, let's say, Laplace u equals f and dxu equals j, dzu equals g. At the corner, of course, I need compatibility between g and j. So I would need dxg equals dzj at the corner. And so we basically have to impose compatibility conditions that are basically this. In addition, though, we have to show that if we impose those compatibility conditions at time 0, that they're preserved forward in time. And in order to do that, what we basically had to impose was that the vorticity vanishes in a neighborhood of the corner. And also, I need G and J to vanish in the neighborhood of the corner. And so under those conditions, then we can build local and time classical solutions. All right, so now let me compare this model that we have on the 3D cylinder to inviscid SQG on a bounded domain in R2. So if I pose inviscid SQG on a bounded domain in R2, I defined, in the case of R2, I defined the velocity as the perpendicular Riesz transform of my scalar theta. But if I'm on a bounded domain in R2, I need a notion of Riesz transform, i.e. a notion of the half Laplacian, and there's obviously more than one way to do this. And so a natural choice, and this is actually what has been pursued in the literature, is to define the fractional Laplacian spectrally. So I look for the eigenfunctions of the normal Laplacian, and I define my half Laplacian and my Riesz transform from there. And Peter Constantine and Mihaela Ignatyeva and Hui Win have indeed pursued this. And they've built weak solutions for the inviscid version of this model and smooth solutions with some dissipation. So they have quite a lot of work in this case. But my question is, how do the boundary conditions that come from the spectral fractional Laplacian relate to the boundary conditions that I found at the 3D level? And if I take the eigenfunctions of the Laplacian on the base of my cylinder, they have to vanish on the boundary. And if I extend harmonically upwards, so I'm in the regime of SQG, that requires my stream function to vanish uniformly on the boundary. So in the context of the three-dimensional model, the boundary conditions that they have are that the stream function just vanishes. And this is not the boundary conditions that we found. So that means that the connection between 2D SQG on a bounded domain and the 3D QG on the cylinder, that connection breaks down here. And it's not hard to see then that the solutions that we build don't coincide with the solutions that they build, basically because we're solving a totally different elliptic problem. All right.
So, I mean, is there a natural fix to what they did that would make it agree with yours?
That's a very good question. I think you would have to choose different eigenfunctions. So, yeah. I think that's what you would have to do. All right. No.
So you're arguing that the correct physical problem is this?
Yes. Yes. All right. Let me switch gears then to non-uniqueness. So the non-uniqueness theorem that I proved is, of course, via a convex integration argument. And many of the features of the iterative scheme are in parallel with other convex integration arguments. So let me not focus on those commonalities, but let me highlight what the difference is when treating QG. And the difference is really in the boundary conditions. So to my knowledge, the majority of convex integration arguments have applied to systems that have periodic boundary conditions. And I have this physical condition at z equals 0 and z equals 2 pi that I need to satisfy. So I can't just impose periodicity there. All right, so the first step in any convex integration scheme is finding the appropriate building blocks for my iteration. And so for me, I have to solve this stationary equation. This is the stationary equation for QG posed at the level of the gradient. Of course, if I'm running a convex integration argument, I will expect the solutions to be defined at the level of the velocity, but the vorticity is, of course, much less regular and not even a function. So I'm building solutions at the level of the gradient. And so I need to find building blocks W. And if I just ignore the boundary condition at 0 and 2 pi, one can calculate that any eigenfunction of the Laplacian is going to satisfy this first equation. And so that's good. I can use the complex exponentials as my building blocks. But the issue is with the boundary condition at 0 and 2 pi. So the best way that I found to satisfy this boundary condition at 0 and 2 pi was to relax this equation in the interior a little bit. So instead of building things which were honestly stationary, I built things which had small errors on the right-hand side here, but satisfied the boundary condition. And let me describe the way that I did this. So the natural thing to do if I'm worried about the boundary condition is just impose that my building blocks vanish in a neighborhood of 0 and 2 pi. So I put a cutoff function in z. So here's z, here's 0 and 2 pi. I put a cutoff function in z. And then instead of plugging in an eigenfunction of the Laplacian into my equation, I plug in that eigenfunction times this cutoff function. And so what I'm concerned about then is what errors this cutoff function introduces on the right-hand side. And one can see that, all right, my cutoff function only depends on z. And so the only difficulty in here is when the z derivative of this gradient lands on the cutoff function. So that term, when the z derivative lands on the cutoff function, it's dzl w, and then I can take L out of this perpendicular gradient because those are derivatives in x and y. So perpendicular gradient of w times L. All right, dzl only depends on z, L only depends on z. I can move them outside of this divergence in x and y. So I have L dzl. When the divergence goes inside, I get 0 when it lands on the velocity. And then here I get the gradient in x and y of w dot product into the perpendicular gradient of w. So the upshot is that when the z derivative lands on L, I have this nice orthogonality which makes this term vanish. So then what happens is that I don't see any derivatives in L on the left-hand side. And so because w is an eigenfunction of the Laplacian, then my right-hand side is just L squared times the curl of some vector field. And I want the right-hand side to honestly be a curl, so I have to move L squared inside of this curl. And then I pay some derivatives on L. And the reason those derivatives in L aren't threatening is because at each step of my iteration, I let L expand a little bit. And I only need it to expand slowly enough that I never hit the boundary. And so I only need the derivatives then of L to grow geometrically. And in a convex integration scheme, the frequencies at each stage usually grow exponentially. So the derivatives on L are much smaller than the errors that are already present in any convex integration scheme. And so then I'm not worried about this term. Or I should say this term. All right, so then finally let me close with some natural questions that one might ask. So the first question is of course related to what you said. So for the cylinder, we started with the no penetration assumption for Euler, and we carried that through the asymptotic limit, but only formally. And in the absence of these lateral boundaries, people have proved theorems for QG, which say that, okay, if I start with the Euler equations and I take the solution to that as that parameter goes to 0, I have convergence to the QG model. And a very natural question would be to show that that convergence holds for our model as well. And then also a natural question considering, I would say, the recent progress on blowup is that perhaps this model exhibits finite time blowup, perhaps related to the accumulation of vorticity near the corners. But that would certainly be a natural thing to ask. And then finally, the non-uniqueness theorem that I proved left a gap in between the preservation of energy and the dissipation of energy. And so one could hope to close that gap. Closing that gap should be strictly easier than settling on Sager for 2D Euler, but so maybe it's doable. And that's it. Thank you all very much for your attention.
In the beginning you talked about density, it's in your equation, but then you didn't mention it. What?
The elliptic operator that you get is actually not the Laplacian. There's a term in the vertical variable that comes from the density. I should have said that. But for the purposes of the presentation, all the results are the same whether or not I have the Laplacian or the elliptic operator.
This is on Z goes to infinity.
Uh-huh.
So what do you assume about density?
You assume that it's decreasing in Z and bounded below from 0.
I was wondering, can you run the convex integration scheme in 2D model? Or is it, so how, when do you do it?
For 2D SQG,
Yeah.
so convex integration for 2D SQG has been addressed by Vlad and Tristan and Steve Scholar.